Bonjour tout le monde, nous sommes maintenant live pour ce webinaire sur l'information quantique. Je vois qu'on a une très grande participation aujourd'hui, de plus de 100 personnes. On va encore attendre quelques secondes que les participants puissent se joindre à nous. Bonjour tout le monde. Hello everybody. Bienvenue à ce webinaire sur l'information quantique organisé en collaboration entre Technomontréal et Intric. Je me présente, Nicolas Godbout, je suis professeur à Polytechnique Montréal et directeur de l'Intric, l'Institut transdisciplinaire d'information quantique. So today we'll have a webinar presentation, an introduction to quantum information given by Professor Bill Coish from McGill University. So before we start, I have a few words. Donc, ça nous fait vraiment plaisir de présenter ces séries de webinaires. Donc, nous avons deux séries de webinaires organisées par Technomontréal et Intric. Donc, cette série sur l'information quantique commence aujourd'hui. Donc, nous aurons une présentation en anglais aujourd'hui par Professeur Coish et nous aurons plusieurs autres présentations qui suivent dans les 2 prochains mois en français. Vous pouvez regarder sur la page web de Technomontréal dans l'onglet « Événements » pour toute la liste. Nous avons une deuxième série de webinaires en photonique quantique. Il y a déjà eu un événement passé que vous pouvez aussi regarder en rediffusion, toujours par le lien par Technomontréal. La série photonique quantique est co-organisée par Technomontréal, Intric, le COPL et Optonic. So the event today is also broadcast live on Facebook, on the Technomontréal page, on the Facebook page. So you can also watch this, and this webinar will be recorded and it will be possible also to watch it later. Donc, ça me fait vraiment plaisir de vous introduire, de vous présenter Professeur Bill Coish, professeur au département de physique de l'Université McGill. So Bill is a Canadian physicist. So I got this bachelor's degree from the University of Manitoba, a master's degree at McMaster University, and then went on to perform his PhD studies in Basel in Switzerland in theoretical physics. So Bill is a professor at the Department of Physics at McGill University since 2010. And he does some work on the theoretical physics of condensed matter. Bill is also a member of Intric. So he's been with us for several years, so has been an active researcher in the field of quantum information. And he will be presenting us today an introduction to quantum information. Before I ask Bill to start his presentation, I will just give you the instructions for the questions. So if you do have questions, we invite you at any time to submit your questions by writing in the Q&A tab that you will find as an icon at the bottom of your screen. Donc, vous pouvez poser des questions à Bill en français ou en anglais à tout moment durant sa présentation. Donc, en cliquant sur l'onglet Q et R. Donc, si vous avez la version française de Zoom, comme moi, au bas de votre écran, vous avez le petit onglet. Et à la fin de la présentation, nous allons passer à travers les questions pour Bill. So, with all this said, I will leave you the floor, Bill.
Merci, Nicolas. Thanks for that introduction. Thank you very much. So it's nice to be able to present this introduction to quantum information. I will do my very best to explain all of the steps, step by step, and give you a few interesting tidbits on what's going on in research right now in quantum information. I hope that if there are any things that are unclear during the presentation, you'll just ask questions at the end and I can try to clarify those points. So the first question we might ask when we ask about quantum information is, what is the basic unit or the element of information in general? And classically, we always think of this bit, a binary digit, as being the unit of information. So we can think of a binary digit as just being a 0 or a 1. We can think of it as being a false or a true statement. We can think of it as being a light switch being off or on. We can think of it as being an extra charge that's on a capacitor or not on a capacitor in some sort of device in your computer or your phone. And a quantum bit is in some sense very similar. And in fact, a quantum bit is a generalization of a classical bit. So a quantum bit can be a classical bit if you want it to, but it can be more. Okay, so a quantum bit or a qubit, it is encoded in 2 levels of some quantum mechanical system. And when I say levels, I'm thinking of the energy levels normally of that quantum mechanical system. You might have a ground state and an excited state. And we can think of those 2 levels as corresponding to the ground and excited states of an atom. We can think of them as being some kind of distinct states of a superconductor where current flows in one direction or another. We can think of them as being the magnetic moment pointing along or opposite a magnetic field for a single electron spin or a single nuclear spin. And so we can prepare a qubit in a 0 state or a 1 state, just like we can a classical bit, but we can do a lot more with it. But to understand what we can do with a qubit, what more we can do with a qubit, we have to look a little bit at the mathematics and see how that works. Before I do that, though, I want to ask the question, how we quantify information in general, classically, for classical bits. And when we talk about the information storage capacity of your computer hard drive or your phone, we always talk about the number of gigabits or gigabytes, or if you're lucky, terabytes that you have available, and bytes are just 8 bits. So we can think of bits. So what we do is we normally count the number of bits that we have available. And the reason we do that is because as we increase the number of bits that are available, we increase the number of different sequences or bit sequences that we can store. So for a single bit, we can store a sequence either a 0 or a 1. For 2 bits, we can store a pair of zeros, a 0, 1, 1, 0, or 1, 1. And so we can, with 2 qubits, we can send 4 different messages, if you like. With 1 bit, we can send just 2 different messages, 0 or 1, true or false. But with n of these bits, we can store 2 to the n different messages. So an exponentially large number of different answers to different questions, or to a single question, if you like. Okay, and so we normally colloquially talk about this very large, exponentially large number of messages that we can send as being just n bits. So if we take the logarithm of this thing, base 2, we say there are n bits of information available in a system of size 2 to the n. But can we come up with a more general measure of information when we don't just have an integer number of bits? And this is a common situation. So one way to think about it is, for instance, if you're restricted to choosing 0 for some reason with probability p, you're not allowed to choose an equal number of zeros and ones. So if you're constrained to a fixed number of zeros in your message, then you necessarily have a smaller number of messages that you can send. The number of messages that you can send is just the number of distinct permutations of zeros and ones, keeping the number of zeros fixed and the number of ones fixed. So the number of zeros here would be p times the total number of bits in the sequence. And so the number of configurations is just n choose pn in this combinatorial factor. And if I take the logarithm of this quantity and say, oh, well, that's my information, the logarithm base 2 of that quantity, again, it scales linearly with the number of bits, but there's this funny extra factor that you get in the limit of a large number of bits.
Yeah, sorry, Bill. I think you prepared some slides with visual cues, but we don't see the screen right now.
You don't see the screen?
Nope.
Oh, I'm sorry.
Let's start sharing.
I'm so sorry. I'm sorry. Okay, so So I was first talking about bits versus qubits, and I think you understood, hopefully, what I said.
Yes.
And then I talked about the number of bits that you can get in a message by counting the number of different possible messages you get for n bits. And then we thought of this as a measure of information, log base 2 of that number, omega. But now if I consider a situation where I'm constrained for some reason to choose a particular number of zeros versus ones, it turns out the number of messages that I can send is reduced, which means that the amount of information I can send with that constraint is lower, okay? And I can still quantify the number of bits per use of my channel, let's call it, in terms of the logarithm of the total number of configurations, and the number of configurations I can get with this combinatorial factor. And so the logarithm I can calculate in a limit of large n using a Stirling approximation, if you know what that is. The limit of large n, I can calculate it as being linear in this number of bits, but it has this funny factor. And this funny factor has a very important meaning in classical information theory. This factor is called the Shannon Entropy. So you may have heard of entropy as a measure of disorder in a system. The Shannon entropy is also a measure of disorder in the sense that it measures our ability to choose from one of many different configurations of a system. Okay, here this is the Shannon entropy just for a single bit. That's what that subscript 2 means. There are 2 possible states. And it's a function only of this probability to choose 1 over 0 or 0 over 1. So p is the probability of 0 in this case. Okay, so let's look more closely at that Shannon entropy and understand when it's large and when it's small. So this Shannon entropy, which characterizes the number of bits per channel use that I can send using this funny channel where I can only send zeros with probability p and 1 with probability 1 minus p. It turns out that this is maximal when I can send 0 and 1 with equal probability, meaning that I have a completely uncorrelated or unpredetermined distribution of zeros and ones. If I select any one of the digits that I've sent or bits that I've sent, with equal probability, it will be 0 or 1. And so the most information can be sent when the system is least constrained, when it's most disordered, if you want. Whereas if I were to force my system to only send zeros, then obviously I can't send any interesting messages because I would just end up sending a long sequence of zeros. I can't really answer any of your questions with that sequence of zeros by introducing some kind of variation. And this parameter p characterizes the probability to choose one value over another, so the probability to lean toward a 0 versus a 1 in my distribution of zeros and ones. And I can, if I want, simulate this same kind of situation with a quantum bit by embedding what I call classical randomness. So I choose a statistical mixture, I say, of zeros and ones, probability p of 0 and probability 1 minus p of 1. Okay, so it turns out that if I choose what I call a statistical mixture, classical distribution, I can do all the same tricks that I could do with my bit, with my quantum bit, just by identifying my quote unquote 0 with this funny object that I call a ket, embedding a 0. This is a quantum bit 0 state with probability p, and then with probability 1 minus p, I have a quantum bit 1 state. But quantum bits are more, they're more than that. I can do something else, and to understand how I do this something else, I need to introduce a little bit of linear algebra. So if I wanted to introduce this concept of superposition for a quantum bit, this is an extra degree of freedom that a quantum bit has that a classical bit does not have, I need another representation of this little ket 0 and this little ket 1. And that representation comes in the form of a 2-dimensional vector. So I can write this 2-dimensional basis vector 1, 0 for a 0, 0, 1 for a 1. And the superposition that I take is a linear combination of those 2 vectors, okay? So with complex coefficients alpha and beta, I can form a linear combination of those 2 basis vectors, and I get a new basis or a new vector, alpha, beta. This is an example of an arbitrary, what I call pure state. So a state that has a definite character about it. I have a definite value of alpha, a definite value of beta. But at the same time, you'll see in a moment when we talk about measurements, quantum mechanically, some things can still be uncertain, the outcomes of those measurements. And if probabilities are between 0 and 1, it turns out the alpha and beta have to obey this relationship. This is what I call a normalization. The modulus squared of alpha plus modulus squared of beta must be 1. And if I have such a constraint, I can always choose alpha and beta up to an overall phase, which turns out not to be relevant, to be parameterized in terms of two parameters, theta and phi. And those theta and phi I can think of as the polar angle and the azimuthal angle for a vector that locates a point on the unit sphere. And when I use this unit sphere to represent a pure quantum state, I call it the Bloch sphere. People who work in quantum optics might know the Poincare sphere, which is a similar object for polarization states of light. Okay, so I can use either this theta and phi, or I can use these complex amplitudes alpha and beta to characterize an arbitrary pure quantum state. And you already see that something is really funny about quantum bits relative to classical bits. Classically, I could only have a 0 or a 1. Quantum mechanically, I'm telling you that quantum states, these states psi, these pure states, they live anywhere on this surface of this sphere. And so in some sense, quantum bits are analog objects. They can occupy any point on this surface of this Bloch sphere for pure states. They can be definitely 0, they can be definitely 1, but they can be anywhere in between. So it's a very funny property that gives us some interesting features when we talk about measurements. So in order to talk about measurements, we have to get into a little bit more detail. So I introduced this ket, which I can represent in terms of a column vector, alpha, beta. And now I want to introduce the dual of that thing I called ket, the bra. The bra goes on the left. So together they're a bra ket, bracket. So the bra is just a transformation of the ket, where I take the angle stuff here and I represent it with angle stuff on the other side. And I take the coefficients and I complex conjugate them. That's the rule. So when I apply the same rule to the column vector, it becomes a row vector, and I take the complex conjugate of those coefficients. So it's a simple rule. I just take the transpose of any ket, complex conjugate, and I get a bra. Okay, so now I can combine these things using standard rules of matrix multiplication. So for instance, I can get this ket-bra combination. So if I try to write this ket-bra combination, the ket is a column vector, the bra is a row vector. And so when I multiply these like matrices, I get 1 times 1 equals 1 in the upper left element. 1 times 0 is 0 in the upper right element. 0 times 1 is 0, and 0 times 0 is 0. Okay, so I can do matrix multiplication, and I get a representation of this ket-bra combination. And this ket-bra combination I call a projector. Okay, it's important for measurements. Now, if I want to describe quantum bits the same way I describe classical bits, in terms of a classical mixture of probabilities, I need some new object called a density matrix. A density matrix can describe pure states. It's just this ket-bra combination or the projector for the specific pure state psi. Okay, I can write that with matrix multiplication again in terms of these coefficients alpha and beta. But I can also write something more general, where with probability pj, I take pure state psi j. And with another probability for every different j, I take a different pure state psi j. So similar to the case where I took, with probability p, I took a 0. With probability 1 minus p, I took a 1 for the classical bit. Now I can generalize to this quantum mechanical mixed state. Okay, so this describes a classical mixture, I say sometimes, of quantum mechanical pure states. Okay, so you've heard all of this formalism very quickly now, but this is a crash course in quantum mechanics that gets you to where you can understand measurements and what happens. So what is a measurement on a quantum mechanical state? Well, a measurement is simply a product of one of these projectors. And the projector is like asking a question. So the question I'm asking here is, what is the probability that my qubit is in state 0? Okay, that's what this projector means. And I act on this density matrix that describes, in this case, this pure state. And then I take the trace of that matrix. So if I multiply this matrix for the projector 0, 0, by this matrix for rho, I find in the upper left element, I get 1 times modulus squared of alpha. And then I'll get an alpha beta star in the upper right. And then I'll get a couple of zeros in the bottom. When I take a trace, I just get the diagonal element. So I just get the upper left element. It's modulus squared of alpha. Okay, and then this tells me the probability that I am in one of those states is 0, that definite quantum mechanical state. But quantum states are really strange in the sense that you can ask different questions and get very, very different answers. So instead of asking, am I in state 0 or am I in state 1, like I would do for a normal classical bit, with a quantum bit, because quantum bits can be in these superpositions, I can ask a question like, am I in a superposition or a definite superposition of being in 0 and 1? So for example, I can multiply the projector for this funny superposition state I call plus. It's defined over here in terms of a linear combination of 0 and 1. I can ask, am I in a plus state in some definite quantum mechanical pure state rho? And there I get this other result. And now if we think of a particular case, for instance, where I prepare a 0 state, okay? If I ask this question, am I in 0? Then with probability 1, I will get the answer yes. I will always be in 0, so alpha equals 1. But if alpha equals 1, because of the normalization rule, I must have beta equals 0. If beta equals 0, when I ask this other question, am I in a superposition of 1 and 0? It turns out I get probability 1/2 of having the answer yes, and probability 1/2 of having the answer no. Okay, so let's review these properties of measurements in quantum states. Oh, sorry, I wanted to tell you one more thing about information. So we might ask the question, okay, if you can put a quantum bit in a superposition, you have an infinite number of points on the surface of a Bloch sphere. So you might think, oh, if I've got an infinite number of points, I can store more information in this object. This is fantastic. I can put an arbitrary state in there, choose any kind of theta and phi I want. And that choice of theta and phi, it must somehow give me more information. The answer is no. And it's because of how the measurements work. Because the measurements always give you yes or no answers, you can't get more than one classical bit of information into a qubit. And we have an object that quantifies this called the von Neumann entropy. It's the quantum mechanical analog of the Shannon entropy that I introduced to you earlier. So this object involves a trace, again, a matrix operation, of rho times the logarithm of rho. And don't worry that you're taking the logarithm of a matrix and then taking the trace of this multiplication. You can do that as long as you diagonalize the matrix. So if you diagonalize the matrix, everything works fine. You just sum over the different eigenstates of the matrix, so the diagonal elements of the diagonalized matrix. And you find that this object reduces exactly to the Shannon entropy with some parameter lambda that's given by the eigenvalue of rho. The eigenvalues of rho turn out to correspond to probabilities, and so they're always between 0 and 1, and this is always a well-defined quantity. And we saw already that this Shannon entropy is maximal at 1 when the argument is 1/2. And so we know that a quantum bit can only ever encode at most 1 bit of classical information. In other words, if I wanted to send n bits of classical information, I would always need at least n qubits to send that information if I wanted to use qubits as the medium of transmission. Can't get more information into a qubit than 1 bit. Okay, now let's review the key points. So key points are that qubits are somehow analog in the sense that you can choose an arbitrary theta and phi. So an arbitrary amplitude of 0, probability to be in 0, an arbitrary phase between the 0 and 1 state to locate a position on the surface of the Bloch sphere. But in some sense, qubits are also very digital because of how they behave under measurements. So if I do a measurement the way that I described it to you, it's called a strong projective measurement. And don't worry about the modifier. One of these measurements behaves exactly as I described it to you. These measurements always yield definite outcomes, true, false statements. So I ask a question, is it true, is it false? In this sense, qubits are very digital. They always give you a yes, no answer. Even though the state before a measurement might have aspects of a 0 and aspects of a 1 because of this quantum superposition, after doing a measurement in this 0-1 basis, I will definitely be in a 0 state if I receive a yes answer to my question, am I in 0? And I will definitely be in a 1 state if I receive a no answer to my question, am I in 0? And with this particular pre-measurement state, I get a 50% probability that I definitely get 0, and 50% probability that I definitely get a 1. And this is a perfectly random process, at least according to the rules of quantum mechanics that we know, there is no way to predict in advance that I would get a 0 or a 1. It is a truly random process, okay? But if I ask a different question, if I ask, am I in a plus state, or am I in the orthogonal state to the plus state, the minus state, for this particular pre-measurement state with 100% probability, I will always get the answer, yes, I'm in the plus state. It's perfectly deterministic when I ask this question. It's perfectly random when I ask this other question. And this perfect randomness is the key to one of the most important current quantum technologies, which is generating true randomness, true random number generator. And you can imagine this is useful to people who want to run online casinos, or people who want to study financial markets, and people even who want to do basic tests of physics or basic tests of the universe. One of the oldest, if not the oldest, quantum technology company out there, Ibm Quantum has made a business of selling these random number generators to interested parties because they know that by the rules of quantum mechanics, if they set their random number generator up properly, it cannot be exploited. This is unlike the case where, at least in principle, a pseudo-random number generator in your computer could potentially be exploited. If the random number generator uses as its seed the clock on your CPU, or it uses some movements of the mouse or some events that happen in your computer, you can imagine that some very, very clever hacker would be able to figure out how to simulate the right movements that give it the kind of outcome, or at least shift the outcome to be more probably in favor of what they want. So Ibm Quantum has been around since 2001, almost 20 years now. There's also another company that's a bit younger in Quebec, Quantum Numbers Corporation, selling random number generators. But you can do much more if you learn about measurements. So if you incorporate now these aspects of measurements that I described to you, it turns out you can do perfectly secure quantum communication protected by the laws of physics. So you may have heard that RSA encryption, the current encryption schemes we use on the internet and in most digital communications, are vulnerable to attack by a quantum computer. So a future quantum computer that could execute an algorithm known as Shor's algorithm can factor very large numbers efficiently. And this is the key to breaking RSA encryption. In contrast, a method of secure communication that was initially proposed by Gilles Brassard at Université de Montréal and Charlie Bennett at IBM in 1984 provides a way to do secure communication without relying on the hardness of this factoring problem. Okay, instead relying on the principles of quantum mechanics holding true. Okay, so we can understand how this works if we just go through the steps that I described in terms of measurements. So imagine that you want to send, or Bob here wants to send a love song to Alice, but he doesn't want anyone else to hear the love song. He's embarrassed, okay? He just wants, it's just for Alice. And so there is a trick we can play, or Bob can play, to make sure that any eavesdropper cannot figure out what are the lyrics to the song if he and Alice share a sequence of ones and zeros that is perfectly random and identical, that they know and only they know. And this is called a one-time pad. So Bob can use this one-time pad, this cryptographic key in red, and he can perform a reversible operation on his song in blue here, called binary addition, to get a message that, provided the cryptographic key is perfectly random, will also be perfectly random to any observer. So anyone who sees it would just see a random sequence of ones and zeros. And this operation is very simple. So if I have a 1 and a 0, I just write a 1. Or if I have a 0 and a 1, I write a 1. If I have a 1 and a 1, I write a 0, or a 0 and a 0, I write a 0. So if the two numbers are the same, I write a 0. If the two numbers are different, I write a 1. And you can see that the end sequence here is something that he might be able to go to the rooftops maybe Alice is quarantining in the next building over, and he can just shout 1 0 0 1 0 0 1 1 0 1 1, and Alice, she hears it, she writes down the sequence. Anyone else can hear it, they write down the sequence. They try to figure it out and they can't figure it out. It's just a random sequence of ones and zeros. But to Alice, Alice has the cryptographic key. She just performs the same operation backwards. So she sees a 1 and a 0, she writes a 1. She sees a 0 and a 1, she writes a 1. 0 and a 0, it's a 0, 1 and 1, it's a 0, and she gets the lyrics to the song. Okay, but what's the key? What's the secret to this ability to share this message? Well, they have to have this cryptographic key. And to share the cryptographic key, they have to make sure that no one else has that cryptographic key, because then they could also decode the secret to the song. So what does Bob do? Bob has decided that he's going to send qubits to Alice. Instead of shouting across the rooftops, he sends qubits, and qubits have this feature that once they're measured, their state is determined. And if you measure in the wrong basis, you flip, or you can get a random outcome that randomizes the state of the qubit, destroys the information essentially. Okay, so Bob sends information, and with 50% probability, he sends this basis 0, 1. And with 50% probability, he sends the plus minus. And I can encode a classical bit in 0 or 1, or I can code a classical bit in plus or minus. And then he just sends those, and he doesn't tell Alice at first or anyone else what basis he chooses for each of the bits. He just keeps sending them. And Alice receives them, and she has to measure them to figure out what's going on. And so she measures also in a random basis, maybe. And she doesn't know which basis Bob has chosen at first. But then Bob can go to the rooftop and say, okay, for the first bit, I chose basis 0, 1. For the second bit, I chose basis plus minus, and so on and so on. And then Alice just records this basis choice, and then she throws away all the bits where she chose the wrong basis, and wherever she chose the right basis, because the outcomes of measurements on quantum bits are deterministic when they're measured in the right basis, she should get the right sequence of ones and zeros. Oh, but what's the problem here? Well, what happens if an eavesdropper was looking at the qubits as they were passing by? So imagine Eve, the eavesdropper, goes and looks at those qubits as they're passing by. If Eve doesn't know the basis that Bob has chosen, Eve will collapse those qubits and randomize them. If she chooses the wrong basis, if she chooses the right basis, they just pass by, no problem. Okay, so Bob and Alice can then check a few of the bits and see, oh, are the bits flipped or are they not flipped? If the bits are flipped, then there's a possibility that the eavesdropper was there and she interrupted the communication, and they know that they should stop and restart the whole process. But if they see that all of the bits match, a large subset of the bits match, then they can be guaranteed up to some accuracy that that they share, only they share the private key. And that's the secret to quantum communication. And this is not just science fiction. If you look at a paper that was published just this past summer in June 2020, a group in China that has been hard at work designing satellite-based quantum communication has reached a distance scale of over 1,000 kilometers at this point, where they send information from Alice to Bob, from one ground station to another. They didn't use exactly the protocol that I described to you. They didn't send bits directly. They used another strategy. And their strategy involved this other word that I haven't introduced to you yet called entanglement. Okay, so on the satellite, they're able to generate strongly correlated quantum particles that they send to these ground stations. And there's a trick that they can play known as quantum teleportation to send qubits from one party to the other without ever physically transmitting light from one place to the other. They only have to talk via some classical channel indicated in this white, and it can be public. And provided they communicate some amount of information, they can convert the shared entanglement into a transfer of one quantum bit from one party to another, quantum teleportation. Okay, but this relies on entanglement. So what is entanglement? Well, this is a picture from Narcisse in southern Manitoba, where I'm from. Well, I'm from Winnipeg, but nearby there is this place called Narcisse. And I recommend, if you're ever in Manitoba in around late April, early May, you should definitely check it out. It's one of the largest breeding grounds of snakes in the world. So they have snake pits where the snakes come every year, every spring. The snakes come and they gather in huge snake balls, and they coil and they entangle. And the same way that these snakes are coiled and entangled and correlated with each other, entanglement represents, in quantum mechanics, a very, very strong correlation between quantum particles. It's so strong that it cannot be reached by classical particles. And this is something that is very tough to conceive of, and it's very tough to explain in a short period of time. But I'll try to show you the formalism that we use to quantify it, and hopefully you get some appreciation for what it is based on what you've learned now in terms of information theory. So entanglement is a generalization of the superposition principle that I already told you about to multiple qubits. Okay, so it doesn't just apply to a single qubit. The superposition principle, now we apply it to multiple qubits. So for instance, we can write an entangled state as a superposition of a definite state of qubit A, state 1, and qubit B, state 0, in superposition with a state 0 of qubit A and 1 of qubit B. Okay, and then the minus sign is not so important. I could put a plus sign here, I can put a phase here, I could put a 1 and a 1 and a 0 and a 0. What's important is that this state here is orthogonal to this state here. So these are two independent orthogonal quantum states in superposition, but they're many particle states or many qubit states. And then I can write a density matrix or density operator the same way I could before by writing the Ket-Bra matrix multiplication that I described to you before. And now I can play a trick. I can say, okay, what happens if someone measures what happened to qubit B and then doesn't tell me about the outcome of the result? What can I know about qubit A? Let's say Bob goes and measures his qubit, and Alice, what does Alice know about qubit A? Well, it turns out that if Bob measures his qubit, he gets 50% probability of 0, 50% probability of 1. And if he doesn't tell Alice what the outcome was, with 50% probability, her state will be 1 if Bob had measured 0. And with 50% probability, her state will be 0 if Bob had measured 1. And so the probability to get either outcome for Alice is 1/2. Okay, this now looks to Alice like a completely mixed state, but we started with a pure state of the joint quantum system. Okay, so mixed states are like classical states. They're just given probabilities of having a definite quantum state. And those states are the states that have maximum entropy. Okay, it turns out that if you maximally mix the reduced density matrix that you get from a pure initial state by tracing out some other part of the system, you get a maximally entangled state. Okay, so that has the maximum amount of information, maximum amount of correlation with the other system. And you can actually generalize this concept, not just to pure states, but general, this measure of entanglement only works for pure initial states, but you can generalize the concept of entanglement to arbitrary quantum states with a different measure, okay? And if you find that this von Neumann entropy is identically 0, it means your state is separable, meaning that the outcomes of Alice's measurements are completely uncorrelated, unrelated to the outcomes of Bob's measurements. We can still have classical correlations and no entanglement, but not for this pure state that I'm talking about, okay? Right, so entanglement means strong quantum correlations. It provides a way of generating correlated outcomes of measurements that wouldn't be possible in classical mechanics. So this is what Einstein called spukhafte Fernwirkung. It's a spooky action at a distance, this weird property that the outcome of one measurement, even though it's separated by an arbitrarily long distance, is correlated with the outcome of another measurement, provided those two measurements are done on the same pure entangled quantum state. And Schrödinger pointed out that there is a really weird effect at work here if we take this concept of, macroscopic quantum superpositions of many qubit or many particle states to an extreme limit. So imagine we have a cat, And the cat is described by quantum particles, so why can't we prepare the cat in a live state that's in superposition with being in a dead state? For instance, by putting the cat in a box with some radioactive decaying isotope, and then the radioisotope at some time scale with 50% probability it will have decayed and 50% probability it will not have decayed, and then the cat goes into superposition of, you know, alive and dead in superposition with the atom. Okay, very weird stuff. But the laws of quantum mechanics, as we know them, do allow this, and provided this happens in reality for large systems, this can be exploited. And so if we can prepare one of these weird Schrodinger's cats with a lot of quantum subsystems, it can be that we can execute certain tasks that wouldn't have been possible otherwise. So as an example, I worked a long time ago now, like 2011, on with some collaborators in Innsbruck, Austria, on generating such Schrodinger's cat states out of a whole bunch of trapped ions. So what they were able to do is to trap a bunch of these individual calcium ions in an electromagnetic trap. There you see them in the little colored dots. So the bright colors are qubits in the one state. The empty spots are not missing atoms. There's an atom there. It's just in a zero state. Okay, so they're doing the readout optically. You can actually see it by your eye, the light that comes off of these qubits when you measure them. But before they measure them, they can prepare them in arbitrary quantum states. And one of the quantum states they decided to prepare them in was this Schrodinger's cat state, where I had to take all the n atoms in the excited state and put them in superposition with all the atoms in the ground state. And we were pretty pleased with ourselves for getting up to 14 atoms. Okay, that was a world record back in 2011. And if you compare to the number of atoms in a cat, it's not very good. But okay, if you compare to 0, it's not bad. So we got up to 14, and that was good. But things have progressed. Things have been getting better and better and better with time. And as we go to larger and larger quantum systems, it turns out that we can get more and more of these qubits entangled with each other. We can exploit that entanglement for practical applications. So say, for instance, you wanted to measure the difference in energy between the excited and ground states of some two-level quantum system. And that difference in energy might be controlled by a local electric field or magnetic field. And maybe you want to, say, measure the magnetic field around a single bacterium, or maybe you want to measure the electric field in the vicinity of some kind of very small nanoscale device, or some condensed matter system. If you want to measure that field, what you can do is you can prepare your qubit in superposition of the 0 and the 1 states, the excited and the ground states here. And then it turns out the time dynamics of that qubit will get an arbitrary phase, not arbitrary, a definite phase at time t, which is proportional to that frequency difference between the excited and the ground states that knows about that local electric or magnetic field. Okay, but now if I can prepare one of these Schrodinger's cat states with n of these qubits, it turns out the phase you get is n times larger. And so in a fraction of the time, you get the same amount of information about that frequency. And this can be used to determine that frequency much more quickly, and potentially learn much more about the electric or magnetic field surrounding some local qubit. You might be using it to sense some biomedical system, or you might be using it to sense some basic material property. Okay, so in principle, the exact same thing can be applied to states of light. So we can think of light as another quantum mechanical system, just like these qubits. And we can prepare these quantum mechanically entangled states of photons the same way we can prepare quantum mechanically entangled states of ions. What happens when you prepare quantum mechanically entangled states of photons? Well, you can do interferometry better. And one very incredible example of this very, very spectacular interferometry is done at the Ligo Observatory, where you have several kilometer-long arms in the interferometer, multiple interferometers, 2 in the US, that are used to measure gravitational waves due to encircling black holes. So it turns out that very, very new work shows that they can improve on the existing measurements by using quantum mechanically entangled states of light in the interferometer, okay? Using a similar trick to the one that I showed you with these Schrodinger's cat states. You can also use entanglement to win at games. Okay, so there's a very nice classic example called Merman's Magic Square, where Alice and Bob, they have some rules that they have to play by. Alice is given an arbitrary row that she doesn't know in advance. Bob is given an arbitrary column that he doesn't know in advance. And then Alice and Bob have to put in plus signs and minus signs. And Alice is told she needs to put in 2 plus signs and 1 minus sign. Bob is told he needs to put 2 minus signs and 1 plus sign. And it turns out that, you know, they don't know what the other is doing when they're putting in their plus and minus signs. And so they have to find a strategy to avoid putting the same, a different sign in the same box. Okay, it turns out classically, if Alice and Bob can't talk to each other, there is no way to win this game every time. You can win it 8 out of 9 times if Alice and Bob use the perfect classical strategy. But if Alice and Bob are allowed to share entangled particles, they can use those strong correlations in those entangled particles to do joint measurements that allow them to win this game 100% of the time. Okay. The real prize, and I just want to wrap up in the next couple of minutes, but the real prize for most of us working in quantum information is not just to play games or to even to improve interferometry, which is already a fantastic thing. The real prize would be a fault-tolerant universal quantum computer. So I mentioned already that a quantum computer, in principle, it could factor large numbers, blah, blah, blah. But for me as a physicist, what I see as fascinating about a universal quantum computer is that it would be a universal quantum simulator. Everything around us in nature is quantum mechanical at its root. And if we want to learn about nature, we in principle need to learn more about quantum mechanics and how things behave, how their quantum dynamics causes them to evolve. And if we had such a universal quantum computer, we could simulate an arbitrary quantum mechanical system and learn about it. Okay, so how close are we to finding this fantastic goal, and why could this work? Well, again, we believe that the root cause, or the reason that we think that a quantum computer will be useful, is entanglement. And a way to see that you can't possibly simulate a quantum computer, if you like, with your classical computer, is to think about the number of classical bits you would need to do what a quantum computer does. Okay, so the number of states that you have, if you want to describe an arbitrary pure state of a quantum system, if you just have 1 qubit, then you only need 2 parameters, the theta and phi that I gave you before. But if you want to describe 2 quantum bits in arbitrary superposition, you have up to, well, of order 4 parameters. It's actually more because they're complex numbers, but it's okay, don't worry about it. It's of order 4 parameters that you need to describe an arbitrary superposition of these 4 different orthogonal states. With 3 quantum bits, you need of order 8, and it goes up exponentially. Okay, and if you even think about storing the quantum mechanical state, a static quantum mechanical state in a classical computer, it becomes completely improbable when you get up to about 100 qubits. So 2 to the 100 is a ridiculous number. For comparison, okay, I think my number is out of date for Google processing by about 2 years or 3 years or so. But at the time when I looked it up, this Google processed about 24 petabytes per day, which is 2 to the 56 bits. Okay, so if you can imagine even a 100 quantum bit quantum computer, just to describe the state, static in time, an arbitrary state would take 2 to the 100 classical bits. It's an unbelievably large number, more than the number of particles in the visible universe. So it turns out that Google has managed to build a 53 qubit quantum processor. Not quite 100 yet, but they're already at the point, or so they claim, where no classical computer would be able to conceivably do what their quantum computer is doing. So you can read here, our Sycamore processor takes about 200 seconds to sample 1 instance of a quantum circuit 1,000,000 times. That's the quantum task they do. Our benchmarks currently indicate that the equivalent task for a state-of-the-art classical supercomputer would take approximately 10,000 years So they did something in 200 seconds that they believed would take a classical computer approximately 10,000 years. It turns out the task they're performing is not necessarily useful for anything yet, but they have demonstrated that there is something their quantum computer is doing that they couldn't possibly have done if they had just tried to simulate it on a classical computer. It's absolutely fascinating. So there are many places you can look if you want to learn more about this stuff. And some of you in the audience will probably have heard about this. The IBM Quantum Experience is a really great place to start if you want to try programming a quantum computer in your own home. I recommend you go to it. It's been in operation since May 2016, but there are some new players in the game. They've just come in. So Microsoft Azure, the cloud division of Microsoft, has introduced Azure Quantum as of November 2019. Again, you can go and from the comfort of your own home, try to code a quantum computer. And they've done this in collaboration with a number of private companies that are building quantum computers of different types. IonQ is building ion trap quantum computers, Honeywell as well. And Quantum Circuits Incorporated is, I believe, doing superconducting quantum computers. I'm not sure. So you can also now look at Amazon Bracket. So they take their name from the bracket notation that I told you about. And they've only introduced this system in December 2019, just launched it in collaboration with Rigetti Computing, which does superconducting quantum computers, IonQ, ion traps, and D-Wave, which you may have heard of as a company in Burnaby, BC in Canada. And so thank you very much for your attention. I hope I gave you a reasonable introduction, but please do ask as many questions as you can in the time available so that I can clarify any points that weren't clear. Thank you.
Thank you very much, Bill, for this introduction to quantum information. I can say that had I seen such a presentation maybe 15, 20 years ago, it could have saved me a couple of years to try to figure out some important concepts in the field. So I think it's a great starter. Now for questions, we already had a question coming in from Andrew. It's a question about quantum information. Supposing a measurement does not collapse the quantum superposition state into a 0 or a 1, but instead preserves the coefficients alpha and beta. So there are several questions relating to this premise. One, is this physically possible? So I will let you answer this first.
Okay, so in some of the examples that I gave, it is absolutely physically possible. I'm not sure if this is the heart of your question, but if you, maybe I should stop sharing so you can see more of me. If you were to project onto this plus state, the plus state is a superposition of 1 and 0 with equal probability. And if you to measure or ask this question, are you in the plus state? It turns out your quantum state always ends up in a superposition. It either ends up in the superposition 0 plus 1 with proper normalization or 0 minus 1 with proper normalization. Okay, so yes, absolutely, you can have a measurement that preserves this coherence. You can get other stuff too, which I did not talk about intentionally because it's a bit delicate and difficult to understand for everyone, I think, who works in quantum mechanics. So there's another concept called weak measurements. So I only told you about strong projective measurements, but there are these concepts of non-projective measurements and concepts of weak measurements. You can look them up, and I think maybe I won't go into details here, but those are the keywords if you want to look it up. It's very interesting stuff, and a lot of research is still being done on that topic.
So there was another sub-question. So again, assuming that we do a measurement and that we can preserve the alpha and beta, would this be more powerful than having measurement outcomes, digital measurement outcomes?
That's a really great question. There are really, really interesting applications of this concept of weak measurements, which I think is kind of connected to what you're asking. So I would recommend, if you want to look at a really neat application, look at Weidmann's bomb. It's a really cool example of where a quantum system undergoing weak measurements. So, okay, I can very quickly say what it is. So if you have an interferometer, and in one arm what you want to do is to determine if a bomb is going to explode, if it's a dud. And you want to do it without triggering the bomb. So if you trigger the bomb, it will explode, and you can't, well, that's a problem. So the idea behind Weidmann's bomb is that if you do a weak measurement with quantum particles by putting the bomb in an arm of an interferometer, it turns out you can determine if the bomb is a dud or not, in some limiting sense, without causing it to explode. It is really phenomenal, and it's hard to grasp. I know it doesn't sound reasonable what I said, but it really does work if you look into this in detail. So look up Weidmann's bomb. It's a really good example.
Okay, and I will continue again with this same question track. Could one read out the coefficients alpha and beta by sampling the quantum states over longer periods of time? So the way I understand the question, is there any strategy where you have this unknown qubit and you can measure over time the actual values of alpha and beta? Is that possible?
Yeah. So with one copy of your qubit, you're in trouble. You won't get more than one bit of information. Remember, one qubit only encodes one bit of information. So you'd only learn one bit of information about the alpha and beta. But if you have many of these qubits, many copies, then in principle, for each qubit, if you do a good measurement, you can get up to one bit of information from every single measurement. And so after n bits of information, you can get a lot of decimal places and accuracy of learning the coefficients alpha and beta. So absolutely, that's something called quantum state tomography that people do all the time.
Okay, but in short, with a single copy of the qubit, you're stuck with the digital answer 0 and 1, or
yeah, I mean, you still learn something because there are certain outcomes that you would not be able to get with certain states. So you can exclude certain states with one measurement, right? But you only get one bit of information about the state.
Okay, so I will go in the Q&R tab. So I would suggest that you ask your questions in this tab. So we already have a queue of 5 questions. A question from Claude. You mentioned cases where there could be classical correlations, but no entanglement. Can you give an example?
Well, I mean, a really good example. Okay, we know about classical correlations already. So a nice example is, say, I like this example of correlations in language. So if you think of the pairs of characters that can exist one after the other in, say, the English language, it's very rare that you would get Q followed by a Z. And so those two letters are anti-correlated, but they're not quantum objects, these letters. They're just classical objects. So there is a different probability to have an I and then an E relative to a Q and then a Z. And so we can write down, if you like, the probabilities for all of those correlations. And actually, if we account for all of those probabilities of all those correlations, we can write down the information per character in the English language, the same way that I did for you in the very specific case where I said, let's just take with probability P all zeros and probability 1, we take, or 1 minus P, we take 1s. We can do the same kind of analysis to find the amount of information in bits per character in the English language. And it turns out you get a little bit less than 4 bits per character, accounting for the correlations and constraints of the language, just the frequency of letters.
Mm-hmm. Okay, thank you. Interesting. So we'll go with a question from Guillaume. How do you actually build a quantum computer? So is it based on standard macroelectronic processes? Is it an optical system? What are the components of a quantum computer?
Okay, so the answer really depends on who you are. There are many versions of quantum computers that are potentially viable. So there are leading candidates right now, if you like. The ones that have shown many qubits are ion trap quantum computers. They've been very good. The best ones so far, if we measure in number of qubits and quality of the qubits, have been the superconducting quantum bits. To make these superconducting devices takes an enormous amount of fabrication expertise. It is not something where you can just sort of buy a 3D printer and put in the code and expect to get a quantum computer out. You need top level clean room facilities and fabrication. So I think all of these implementations of quantum computing, ion traps, superconducting qubits, say spins in semiconductor quantum dots, they all require very high level fabrication, and they all have different trade-offs. So it's really a different answer for every different system. But for 100% of them so far, you need an enormous facility. So you cannot imagine doing this in your basement, if that's the question.
Okay, so I see that time flies and it's already noon, just told noon. So if Bill, you're available, we can stay online for another few minutes and continue going through the questions.
Yeah, no problem.
Okay, thank you. So we have a question also from Denis. Does McGill or maybe other entities offer summer schools in quantum computing or for newcomers in quantum information science?
Yeah, so there's a really good summer school that's run by a different Canadian institution every year, is the Canadian Summer School in Quantum Information. So you can look that up if you are a university student. So normally it's for people who are in graduate studies, but sometimes undergraduates who are working with a supervisor that is connected with the summer school can get to go. So that is a really good one. There is also, if you're lucky enough to be an Intrigue student, there is a really good student-run school called Conférencier that I highly recommend. But for that, you have to find a supervisor who is a member of Intrigue already or is affiliated in some way. So, look for a supervisor. And if you're a good student, I think, that's a great path. There are a number of other summer schools, and I can recommend them to you. If you want to send me an email, I'd be happy to send recommendations.
Yeah, good point. So we could also accept questions, later questions for more details. And maybe a last question. Bill, since you're a professor at McGill, maybe you could tell us what is the expertise, the strongest areas of expertise at McGill related to quantum information science?
So we have really, really good people working in quantum sensing. So Professor Lily Childress and Professor Jack Sankey, they work in quantum sensing with single spins in diamond, of all things. They can find the local magnetic field on a nanometer scale. It's an extremely good area of expertise. My own group, we work largely on spins as well, spins of electrons in quantum dots or in at impurity atoms. So like these nitrogen vacancy centers in diamond, the ones I mentioned, spins in diamond. There are people who work in low temperature physics, quantum properties of low temperature condensed matter systems with applications to quantum information. So very low temperature states, funny exotic states of electrons that behave in a very weird quantum mechanical sense. And there is expertise also in other departments, in engineering, for instance. There are people who work on devices, quantum devices, from an engineering point of view. And there is, so Claude Crépeau is perhaps still in the computer science department at McGill, working on quantum communication. And he was one of the early people who worked on quantum teleportation, and now works on a lot of interesting problems associated with these quantum games that I mentioned.
Yeah, thank you. So yes, lots of local expertise. And I really thank you, Bill, for having shared your understanding of quantum information for this general audience. And I hope that you all enjoyed it. We'll be having other such seminars, and we really like the turnout. Thank you, everybody. Thank you, Bill.
Merci, Nicolas.